Okay, so the next set of slides is going to be about policy gradient methods. And then this is a set of methods that has become quite important in recent years. In part, if you want to tackle environments with continuous actions, then they can be quite effective. Okay, so I'm going to talk about stochastic policy gradient and a classic algorithm known as the reinforced algorithm. And then to give you some example, I'll describe how Alphago essentially used policy gradient methods initially to obtain some very good results. Okay, so as a quick recap, we just talked about Q-learning. And if you recall, Q-learning is a model-free, value-based method, right? So it's model-free because we never end up estimating any distribution of states given previous states and actions. All we do is instead estimate a value function. So it might be the value function v or the q function q. But then we also do not have any explicit representation of the policy. If we want to extract a policy, then we use a q function and then we simply look up which action has the highest value. Okay, so that's what we've discussed so far. This has been our main algorithm. But now we're going to see another class of algorithms that are known as policy gradient. And these algorithms, the main difference is that now instead of being value-based, they're going to be policy-based. Okay, so you see, it's one thing to be able to represent a value function and then extract a policy. But then since the goal anyway is to obtain a policy, why don't we represent the policy and why don't we optimize the policy directly? So policy gradient techniques will achieve that. And interestingly, in their case, what they do is they drop the notion of a value function. So we're going to work with a policy representation only, and there won't be any value function representation. Now later on, we're going to see that there are algorithms known as actor critiques that actually have both. But for now, we're going to concentrate on policy gradient techniques that only have a policy representation. Okay, so the easiest when it comes to policy gradient method will be to consider stochastic policies. There's a good reason for this, is because if we want to compute the gradient of a function, it's actually a lot easier if this function is continuous and smooth. Now, if we have a policy and we want to compute the gradient of that policy, and this policy works with discrete actions, then it would be a discrete function, and it would be very hard to come up with a gradient. So one way to make the policy continuous and then obtain a gradient naturally is to essentially consider stochastic policies, right? Because if I have a stochastic policy, then the output is not really a discrete action. Instead, it's going to be a probability, which is a number between 0 and 1, so it's a continuous function. Okay, now, when I parameterize my stochastic policy, I'm going to use theta to denote the parameters. And here, theta could correspond to the probabilities themselves, but more generally, it will look more like something along those lines here. If I have discrete actions, then often one way of representing my policy pi will be to consider what is known as a softmax function. So a softmax function, this is something quite popular in neural networks. Whenever you want to have some output that is also a distribution, then what you do is you take whatever values you have, raise them through an exponential, and then divide by the sum of all the exponentials of all the values to normalize. Okay? So here, the idea is that since a probability should be positive and between 0 and 1, when I take the exponential, here the exponential will ensure that I always have something positive. And then when I divide by the sum of all these exponentials, then I'm going to normalize and I'm going to make sure that the output is necessarily between 0 and 1. Okay? So that's how you can think of this as a nice function, and it's called the softmax because we can think of this as also an approximation to whatever is the maximal value. Okay, so here in this expression, I've got another function called h, and here h, just think of it as a score. Okay, so it's going to be a score, and this scoring function might be computed either through a linear function with respect to theta, or maybe a nonlinear function like a neural network. Okay, so these would be the two most popular types of scoring function. If it's linear, then what will happen is that theta will essentially be a vector of parameters, and then I'm going to multiply each parameter theta by a basis function. So here f of I is simply a basis function that returns a value for every state action pair. So that's a generic way of encoding the scoring function when it's linear, but more generally we'll want to also consider nonlinear scoring functions and therefore neural networks. Okay, so this is for the case of discrete actions, and now if we have continuous actions, we're going to see in a moment that we don't have to make the policy continuous, we don't have to make the policy stochastic in order to obtain a continuous function, because if the actions are already continuous, then we have a continuous function. But it will be easier, at least for now, to consider still a distribution over these continuous actions. And what is quite common is to consider the Gaussian function. So the Gaussian function, right, would look like this. So I have a distribution over my actions, and then this will be determined by a mean and a covariance matrix. And then the mean and the covariance matrix would depend themselves on the states and also some parameters theta. Okay, so that's what this represents. Okay, so now before I go on and explain how to do reinforcement learning using a policy gradient technique, it's interesting to just take a step back and look at now, what if I was able to do supervised learning? Because if I have a policy that's represented by some function, pi theta of a given s, right? So my stochastic policy is represented by this function. Now, if I happen to be able to do supervised learning, where for every state I have an oracle that tells me what is the best action, then I can do supervised learning in the sense that I can simply maximize the log likelihood of the actions. Okay, so here I'm using star to denote that A1 is the best action for S1. Here A2 is the best action for S2, and so on. So here I'm making an assumption that these actions are optimal. If they are optimal, then I know what I should pick, and what I really would like to do is simply to maximize the probability of the optimal action given each state. And then one way of doing this is to set up an optimization problem with an objective here that could correspond to just maximizing the sum of the log of those probabilities. Okay? So yeah, for anybody familiar with supervised learning, right, this should be quite natural to do. And now with this objective, we can simply compute the gradient and take a step in the direction of the gradient. So if we do that, here we would take the gradient with respect to the log of the policy, and then we would simply take a step alpha n, so that's our learning rate again. Okay, so that's what we would do. Now let's compare that to reinforcement learning. So in reinforcement learning, we would have again a policy pi. It's going to be parameterized in the same way. The difference is that now I don't have the correct action or the optimal action for every state. Instead, I have a state, I have an action that I tried. I don't know if it's the best one, but the environment gives me a reward, right? So the reward essentially is a signal that tells me perhaps how good this action is, or at least how good would be all the previous actions. So So now this is a weaker signal, right? Because I can't use supervised learning because I don't know what is the optimal action. But on the other hand, I've got this reward, which is a numerical signal that I can use to drive the learning. And here, what we discussed before is that what is natural to do is to try to maximize the expectation of the future rewards with perhaps a discount factor. Right, so at every step, I'm going to obtain a reward. This reward might be stochastic, so that's why here I've got an expectation. And then the reward would depend on the current state and action, but then the current state itself depends on the previous states. So again, this expectation here is with respect to both the rewards and the states. And then I have to discount here for every step. Okay, so this is my objective in the reinforcement learning. But now if we simply take the derivative with respect to theta to obtain a gradient, then we obtain the following update. And now if you look at this update, this is very interesting because we have again the gradient of the log of the policy. But what's different is that now we have here gamma to the n times gn, where here gn, I'm going to define it as simply the Monte Carlo estimate for the sum of the discounted rewards in one trajectory. Okay, so what's really interesting is that this notion of policy gradient, because here we are computing the gradient with respect to the policy, but with respect to a different objective than the one for supervised learning, it gives us an update that is very similar to the one that is obtained in supervised learning. So we have this term that is in common, right? So if I just go back, right, you see we had this term here, but now I'm going to insert in between gamma to the n times gn. And the intuition here is that I don't know what is the best action. So on the other hand, what I know is that after I execute an action, I obtain some rewards at every step. And if I sum up those rewards, that gives me a numerical signal. And then perhaps the higher that signal is, right, then the better that action is. And maybe this would indicate that I should increase the probability of this action in a way that's proportional to how good were all those rewards. And that's exactly what we're doing here. Okay, so the intuition here is that, you see, I don't know what action I should take, but I have a numerical signal in the form of rewards. I add up all of those rewards, and then the higher that signal is, perhaps I want to make a bigger update. And then so that's why I'm going to multiply my gradient here by the magnitude of this signal. Okay? So that's the main difference. But now I'm going to explain how we derive this. Okay? So this is the nice analogy so far between reinforcement learning and supervised learning. But then, yeah, the derivation of this is not so simple. Okay, so to derive this, I need to introduce a theorem that is known as the stochastic gradient policy theorem. So here, the idea is that we are trying to maximize expected rewards, right? So if I just go back, this was my objective here. And this objective is really just the value function of the policy. So I'm really just trying to maximize my value function. Right? So if I want to maximize my value function, perhaps what I could do is simply compute a gradient with respect to theta in my value function, and then simply make a step in this direction, in the direction of that gradient. Now, this theorem, the stochastic gradient policy theorem, says that this gradient is going to be proportional to this expression. Okay, this expression is essentially the Q function times the gradient of the policy. I'm going to have an expectation here with respect to actions. And then I also have an expectation with respect to states, where this mu theta of S is going to be a stationary state distribution when I execute the policy that's parameterized by theta. Okay, so here I'm going to define this on the next slide mathematically, but just intuitively, right? This expression, think of it as like I execute my policy, and then I just observe which state I end up in. And then if I'm going to form a distribution that corresponds to how likely I'm going to end up in any possible state, it would be precisely this distribution. Okay, so this is known as the stationary distribution, where if you execute the policy forever, or otherwise if there is a termination, so till the end of the policy, right, then there's going to be some probability that you'll end up in different states, and that's this distribution. Okay, so we don't have this quantity, which is going to be an issue, but we're going to resolve that through sampling. And for now, the key is that I'll show you how to derive this expression, because this expression is effectively telling us the direction of the gradient. Right? So the gradient is proportional to this, so it means that this is giving us the direction of the gradient. Okay, so here's the derivation. So when I take the gradient with respect to theta in my value function, then I can do the following algebraic manipulation, and then at the end I arrive at this expression. Okay. So very briefly, what I'm doing is that first I expand V, so we can think of V as really being the Q function, where I'm going to execute certain actions according to my policy. So that's why here I have an expectation with respect to the policy. Then after this, I apply the gradient to the bracket. Now theta appears in a product, so that's why I've got now the gradient of pi times q plus pi times the gradient of q. Okay. Then after this, I simply expand q. So q is going to be an expectation for the current reward plus the future rewards. Then I can apply the gradient to this expression. Now, because I'm looking at the gradient only with respect to theta, here theta doesn't appear in r, so I can drop r, and I'm only left with v theta. So it's this expression that's left here. Then after this, let's see. So what I do now is I'm going to expand this. So you see I have again the gradient of v theta, which is what I started with. So I'm going to simply unroll this expression, because this is a recursive expression. So I now unroll it, and then that gives me now a bigger expression. And when I unroll it like this, I can start gathering the terms, where every term is going to have the policy times the q function. So in fact, the gradient of the policy times the q function. So I have it here. I have it in this term as well. So you see I've got the gradient of the policy times the q function. And then if I was going to expand this further, this would occur another time, and so on. So now all of these, I can gather them together, and now what's in front is the probability that I would reach a certain state x by time step t according to my policy that's parameterized by theta. Okay, so here this is the probability of reaching x from s at time step t. Okay, and once I've got this, then I can write this expression, and it turns out that here this summation with the probability of reaching some state x according to my policy theta, it's essentially looking at the probability of all the states that I can reach, and it's my stationary distribution mu theta. So earlier I said that I would define what mu theta is, so it's implicitly defined from this line to that line, right? So mu theta of s is essentially this double summation with the probability of reaching x. Okay, so yeah, so that's how I arrive at the gradient policy theorem. Any questions regarding this?
Sorry, what's the x again?
So here x is just another state. I need to distinguish x from s, so that's why I'm not using s, but it means that it simply means that it's a state. Okay. All right, so now based on this theorem, what we can do is simply drop these summations, because these are really expectations, and then I can approximate these expectations by samples. So I'm going to do a one sample approximation for each expectation, and then I arrive at this expression here. Okay. So in fact, yeah, here what I do is those summations are essentially rewritten in terms of an expectation here, and then this expectation, when I drop it, then I can get a one sample approximation, and this corresponds to just doing stochastic gradient descent. So, okay, this was a bit of a derivation, but it's an important derivation because it justifies essentially how we can update our policy in a way that is very close to supervised learning, but with the difference that here I have gamma to the power of n times gn. Okay? And it's this derivation that shows that. Okay? Okay, so we can now put this into an algorithm. So this algorithm is in fact quite old. It dates from, I believe, 1992. And it was called the reinforced algorithm because it was, I guess, one of the early reinforcement learning technique. Obviously, there are many other algorithms that are doing reinforcement learning, but that one, at least back in the days, there were not so many, it was called reinforce. Okay, so the algorithm starts by initializing the policy pi to anything, and then you do this loop. So in each iteration of this loop, you're going to go through an episode, and then in the episode, you generate a sequence of state, action, reward, and so on. And then for an entire episode, you can compute what is the sum of the rewards, and then use that in the update. Okay? So here the reinforced algorithm is really doing an update to the policy that's based on essentially a Monte Carlo estimate of the value of that policy. Right, so I told you at the beginning that this algorithm would not have any type of value function representation. And indeed, when you look at this, there is none, but it achieves that by essentially using Gn, which is our Monte Carlo estimate of the value of the policy. Okay? So that's not going to be the most efficient algorithm, but it is one of the simplest algorithms and one of the oldest algorithms for policy gradient. Any questions? Yeah.
So here we also have to complete the episode before doing updates?
That's right. So yeah, so here you do an entire episode. Once you're done, then you can start doing some updates. And then you're going to do multiple updates per episode because this Gn, right, is going to be the sum of essentially all the future rewards. But then you're going to do one of those updates at every step. But yeah, one of the problems is that you have to wait till the episode is completed so that you can do this summation. Okay, so it turns out that this algorithm was in fact key to the success of Alphago. So again, I've got here as an example the game of Go. Very simple game, at least simple in the sense of the rules. So there are two players, white and black. They alternate in terms of putting down a stone. And then the goal is to surround as many intersections as possible to essentially create your own territory. And whoever has the largest territory wins. Now, this is one of the oldest games and one of the hardest games for humans to play. And then there's always been some interest to develop some computer software, so some algorithms that could play this game well. And this is an interesting chart that shows sort of progress. So on this y-axis, we've got some ratings. So this is beginner, amateur, professional. And then some of the older programs were not very good. They were playing at the beginner or amateur level. But then something changed. So Alphago came along, and then it played at a professional level. And not only did it play at a professional level, but I've got here Fan Hui, who was one of the best players in Europe. And then Alphago defeated Fan Hui, so this was one of the first important games between a computer and a professional player where the computer won several games. Okay, so what happened is that up until Alphago, the state of the art was to use Monte Carlo tree search. So we're going to see this technique. In fact, Alphago still used Monte Carlo tree search, but it did it in conjunction with deep learning. And in fact, it was using a policy gradient technique. Okay, so just a bit of history. So in 2016, Alphago defeated Lee Sedol, so he was one of the top players in the world from Korea. And then at the time, the top player, his name Kejie, he was a world champion. He said, Alphago can't beat me. But then in May 2017, Alphago defeated him as well. And at that time, he made a comment and he said, well, last year Alphago was still quite human-like when it played, but this year it became like a god of Go. Okay? In any case, what really happened is that, there were advances with respect to reinforcement learning and deep learning. And now let's look into the details of what was the approach to win. So at least at the beginning, so now there's been several versions of AlphaGo. There's AlphaGo and then AlphaGo 0 and then at some point Alpha 0. But now if we just focus on AlphaGo, so the first important version had 4 steps, where the first step, they actually did supervised learning with a policy network. Then after that, they have employed a policy gradient technique, still with a policy network. Then they use a value gradient technique with a value network, and then they combine that through a search technique. Okay, so a policy network was essentially a neural network that encodes a policy that would indicate with what probability AlphaGo would select an action given a board configuration. So here S is a state, and that corresponds to a board configuration. And then A is an action, so it's essentially the next position where you would put down a stone when you play. Okay, so now here we consider stochastic policies. So the output is really a distribution over actions. So basically there is a neural network that would output a distribution over all the intersections. There's 361 of them when you look at the entire board. Okay, and then the main approach at the beginning was to say, well, we already have lots of data that comes from experts that play the game. So can we do supervised learning and simply train a policy network to mimic how a human expert would play this game? So to do this, then they use as data so pairs of a board configuration with the play that is recommended by an expert. And then, as I explained before, for supervised learning, you can simply maximize the log of the probability of the correct action given the board configuration. And then you would have a simple gradient, and then you would simply do an update in this fashion. Now, we want to go beyond human expertise. So AlphaGo could not have defeated all these human experts just by learning to play like them. It needed to go beyond what they were capable. Okay? So one approach was to use a policy gradient technique. And then in this case, we still have our policy network. That's again a mapping from board configurations to distributions over actions. And now the difference is that instead of just looking at what action or what play an expert would make, you essentially play the game and then observe what would be the sum of the rewards till the end of the game. Now in the case of Go, there's many ways in which you could compute rewards, but it turns out that the simplest is just to say that you earn a reward of +1 when you win, and you earn a reward of -1 when you lose. Okay? So this entire sum ended up just being +1 or -1. Okay? And then you can apply the gradient that we derived earlier, so the reinforced algorithm, and do an update based on that. So now this provides a way for AlphaGo to essentially train itself by playing against itself and then recording what would be the moves throughout the game. And then if it wins, then it can do an update in this fashion. And then if it loses, you see if it wins, this will be +1. And then essentially the probability would increase for this particular action. And if it loses, then this would be -1, and then the probability would decrease. So that's the idea. Okay, so as I explained, for each game, the sum of the reward was just +1 or -1. And then again, these are the updates that were made. And then in this case, there was no need to use any discount factor because the game is episodic, right? So there's an episode where you can play until it's over, and then it stops at that point. Okay, so the third step was then to also train a value network. So AlphaGo used a policy network trained by supervised learning and then refined by a policy gradient technique, but it also trained a value network. So the value network is very similar. It takes a board configuration as input, but the difference is that instead of outputting a move or outputting a distribution over possible moves, it would simply output a score, effectively here a score that should be either +1 or -1, so it tries to predict whether from this board configuration it would win or it would lose. Okay? So the value here is the sum of all the rewards, and then in the way this was defined, right, the sum of all the rewards will either be +1 or -1 depending on whether it wins or loses. So then here there's a neural network that will output for every board configuration a number ideally close to +1 or -1. Okay, and then so this was trained simply by, again, just observing when you play the game till the end, whether you win or lose, and then you can simply take the Euclidean difference, compute the derivative, and then do a weight update. So this is essentially the Monte Carlo technique that we saw at the beginning for learning a value function. So it was used by AlphaGo as well to obtain a value network. Okay, and then the last step was to combine these two together through a Monte Carlo tree search. So here the idea is that you have the policy that can guide what action to select, but then if you explicitly enumerate the possible moves up to a certain depth and a certain width, then you can get some estimates that are more precise. And then so we'll see later in the course this particular technique known as Monte Carlo tree search. And then so it allowed AlphaGo to essentially combine together both this policy network and this value network and obtain something that was even better. So in any case, I won't go into the details yet of what is Monte Carlo tree search. We'll reserve that for some upcoming lecture. But in any case, that's the last piece missing. And for now, you should be able to understand quite well the rest of the approach. Okay, and just to conclude, so here in this competition, Alphago played various games against Fanui. This was the European champion. And then, so we've got some of the results. And then what I described was essentially the version of Alphago that was used to play against Fanui. Now, after that, it was improved significantly. And that's not reflected in what I explained here, but at least I'm telling you this because this is a nice example of where these techniques that we just saw have been applied quite successfully. Yes?
How would Alphago resign?
Oh, how did it resign? Okay, yeah, that's a good question. So I'm not an expert. So, okay, roughly speaking, when you play Go, at some point, the two opponents will look at the territories that they own, right? And then it becomes quite clear that one owns more than the other one. And then when you resign, you basically just admit that, okay, it doesn't matter how much longer you would play, you don't think that you're going to essentially capture a larger territory. Now, how exactly is this determined? I'm not entirely sure. I'm going to guess that what AlphaGo did is to essentially perform some simulations where it would, I guess, try to foresee what would happen if it continued playing. And perhaps those simulations indicated that it just wasn't going to win. Yeah. Yes?
Wasn't the value function you just spoke about like an estimate of the probability of winning? So you could just have a rule that said, if I think the probability of you winning is less than 10%, then I'll just resign not.
Yes, that's a good point. So yeah, the value function would normally output either a +1 or a -1, but we could interpret this as a probability or at least some notion of how close we are to win or lose. But I don't know. I guess, yeah, that it might use this as well. I'm not entirely sure. Yeah. Yes?
We calculate as the G, the Gn, as we need to prepare for all the reward for every step that from the end step to the very end step. So that we have set as the very end step that's reward as the -1 or +1. So what about the reward that's between and the end of the
Right. Okay. So yeah. So Gn, which is the sum of all the rewards, in the case of Go, the rewards were defined in such a way where there's 0 reward at every play until the end of the game, and then at the end of the game, there's a +1 for winning and a -1 for losing. Okay. Now, obviously, this is extremely simple, and then in other games and in other scenarios, you would typically have rewards at every step, but in this particular case, there were no rewards effectively until the end.
And also, that we need to prepare for the episode for every pair of the actions and the states. So when through the game go, I think there's maybe billions of states. So how should we prepare this for you?
Yeah, so here there's definitely lots and lots and lots of states because the number of board configurations is effectively 3 to the power of 361. But here it does not enumerate all of those states. Instead, it uses a neural network that approximates, and then so it will essentially train itself by having some state actions, state triples. And this will really just be a sparse number or a very small number of all the possible states, but then it will more or less interpolate based on that using a neural network. Yeah.
So is the game of AlphaGo still a Markov decision process?
Is the game of AlphaGo a Markov decision process? So I guess not. so here, okay. It's really what would be known as a minimax game because you have two opponents, right? And then Normally in a Markov decision process, what happens is that you have the agent, and you could say that you have nature, and nature acts stochastically. And nature is not trying to defeat anyone or anything like this. So here in this game, or in fact in most games where there are some opponents, using a Markov decision process is indeed questionable. Because in this case, the opponent might not be acting stochastically, and in fact will try to minimize the score of, well, try to minimize your score. So this is where tools from game theory are often useful, but it turns out that in this case, it was okay. And then so the idea is that through reinforcement learning and function approximation, it was able to interpolate and obtain some good approximation for the policy as well as the value function. But yeah, there is a risk that it might think that the opponent will act in a certain way, but really it doesn't. And then, yeah, that might not be the best approach.